Finally, we turn to a management protocol that is specialized and optimized for one particular purpose. The protocol in question is Netflow, a very similar protocol called IPFIX, or IPFlow Information Expert pronounced as IPFIX. With the same technical goals, it is currently under development by the IETF Standards Organization. We focus our discussion on Netflow because it has a wide deployed base today, but you will find that the discussion carries directly over the IPFIX. Netflow was first introduced by Cisco and is geared toward collecting data about networking traffic from a device. You can use this data to answer questions such as the following. Who are the top talkers in the network? How much traffic is being exchanged between two destinations? How are links in the network being used? Or where are the traffic bottlenecks in the network? In theory, the collection of such data could also be attempted through a more general-purpose management protocol. However, a big challenge is posed by the fact that large volumes of information need to be collected and transferred. Because Netflow and IPFIX are specialized for this particular application, they incur less overhead and are more efficient than other management protocols that have to serve the purposes as well. IPFlows. Netflow communicates statistical information about IP-based data traffic that flows over a router. The statistics are provided on a per-flow basis. A flow consists of all traffic that belongs to the same connection context, basically IP data packets that belong to the same connection. Of course, IP is completely packet-based and has no notion of a connection that is its whole point. However, chances are applications that communicate with each other using IP will exchange in general more than one packet when they start communicating, as Figure 8-15 illustrates. For example, a file transfer application breaks up the file that is to be transferred into many individual packets. All the packets that belong to the same transfer and need to be delivered over the network, and all might flow over the same router. The same is true for an image that is transferred for viewing a web page, or for a voice-over IP conversation carried out between two users. Therefore, if a router sees one packet coming from and going to a certain direction, chances are there will be others. This is what is meant by a flow. Of course, in some cases, a flow will indeed consist of only a single packet, but typically, there is more than one packet to flow. A flow is uniquely identified by the following pieces of information. In database parlance, they would be considered keys: source address, source port, destination address, destination port, protocol type, type of service or TOS, byte. A byte in IP that identifies the type of service used to differentiate different categories of traffic. Input logical interface, identified by the same index that is used for the interface in SNMP MIBS. This is needed because, in addition to the source address and port, in the case of private networks with private IP address spaces, the other spaces of information might not be unique to one flow. Data that is collected for each flow constitute a flow record. It includes the keys that identify the flow, as well as the time when the flow started, when it stopped, and how many packets were transported as part of the flow. This data is extremely useful for management applications that offer accounting and performance management functionality in several ways. Knowing how much traffic of what type was sent at what time from where to where allows network managers to account for detailed network used by individual users. This is important if a network provider wants to charge based on actual traffic consumption instead of charging simply a flat access fee. Of course, As traffic flows across multiple routers, the network provider must be sure to avoid double counting the same traffic on multiple counters. This can be ensured by correlating flow records that are collected on multiple routers, or by making into account only the flow records generated by the access router through which a particular user is known to connect to the rest of the network. It provides a wealth of data for traffic analysis, bottleneck, and network planning. It can provide an invaluable tool to spot and defend against attacks on a network that carry certain characteristics in terms of the traffic patterns they generate. Netflow protocol. On an individual router, with traffic coming from and going to all kinds of directions, at any point in time there may be tens of thousands of flows in progress, depending on the router's capacity. This obviously leads to a huge volume of flow that needs to be collected and transferred. At the same time, the data is extremely uniform. Basically, it is the same data that is of interest for each flow. Hence, there is only one type of record to be transferred. This observation is what motivated the introduction of a dedicated special purpose protocol rather than attempting to use a more general mechanism such as SNMTP or syslog. This protocol simply consists of putting flow records into Netflow packets and exporting those packets to a recipient. The recipient of Netflow packets is commonly transferred to as a Netflow collector. Similar to a logging host for syslog, the task of the Netflow collector is to store the data that is put out by the routers at a very high rate and make that data available to the number crunching applications. Figure 8-16 illustrates how a Netflow packet is structured. It consists of the following elements. A header contains bookkeeping information. The sequence number of the packet for storing packets that are received in the proper order and determining whether any data is missing. The number of flow records contained in the Netflow packet. The version number of the Netflow protocol itself. The header is followed by a sequence of flow records. Each flow record includes the keys that identify the flow, as well as the statistical data collected for it. Now, how is the flow managed inside the router? When a packet with a new combination of the 7 keys, source and destination IP addresses and ports, TOS, byte, protocol type, and input logical interface is detected, a new flow is entered into a special store on the device, called the Netflow cache. In this cache, data about the flow is maintained. For example, a packet counter is incremented as packets belonging to that flow go by. Incidentally, the data in the cache is used for other purposes. Specifically, it facilitates the routing decision for packets on the flow. Simplistically, the router sends subsequent packets that belong to the same flow in the same direction as the earlier ones, without needing to make more complex individual routing decisions for each packet. When the router determines that the flow has ended, the corresponding entry in the Netflow cache expires. This means that the information about the flow is flushed from the cache and the flow record is prepared for transmission using the Netflow protocol. A flow is considered ended in these circumstances. No traffic has been detected on a flow for a certain time interval, typically 15 seconds, but ideally configurable. A packet is detected at the application protocol level that indicates that the data transfer supported by the flow has completed. For example, in case of a TCP connection, this is indicated through TCP FIN or RST packets, two special kinds of packets that are part of the TCP protocol. If a flow has been going on for a long time, eventually the router simply declares the flow ended and starts a new one. Otherwise, it would be impossible for the Netflow collector to be informed of the flow, even though it might represent a significant amount of traffic over the network. Using telephone analogy, this would be like talking to someone overseas for months without ever putting the phone back on the hook, and therefore, if an accounting record were generated only upon completion of the call, never receiving a bill for it. Finally, it needs to be mentioned that as with SNMPs, several versions of Netflow exist. Netflow version 5 is the version most commonly used today. It has all the capabilities that were discussed here. Netflow version 7 is geared to switches, not routers. Netflow version 8 offers an aggregation capability. This allows it to be configured on a router so that it combines the data from several flows into one record. For example, summing up all traffic from one source regardless of the destination. This reduces the volume of Netflow data being exported and makes collection easier. Netflow version 9 is the newest version. It allows the records that are exported to be customized using a greater selection of different statistics that can be collected. The record format that is being exported from the device is defined using a special template. The protocol is enhanced to allow for transmission of that template in addition to the flow records themselves, so that Netflow sender and receiver are always in sync on what the data that is being exported actually represents. Finally, as mentioned in the beginning, the IETF Standards Organization is in the process of standardizing a protocol with the same goal as Netflow, called IPFIX. In fact, the possibility exists that IPFIX will end up looking remarkably similar to Netflow version 9. From a technical perspective, the goal and general principles are virtually the same. The more important difference is political, in that IPFIX will be endorsed by an open standards organization, whereas Netflow constitutes a de facto standards with a large installed base but whose specification is owned by a company. In summary, Netflow is a special-purpose management protocol that is used to collect large volumes of statistical data about networking traffic defined as flows. It is the basis for many performance and accounting management applications. Several versions of Netflow exist. Version 5 is the most commonly used, and version 9 has the widest functionality. IPFIX is a sibling protocol to Netflow that is defined by the IETF. It has the same goals and very similar capabilities. Okay, that's all for our Netflow and IPFIX lesson. Thanks for listening.